Welcome to lecture 35. In this lecture, I will talk about the Friedmann equations that we will use for our studies of cosmology. Recall that we have the field equations of general relativity, which are given by the geometry part, so Ricci tensor, Ricci scalar, and cosmological constant on the left-hand side, and the matter part represented by the energy momentum tensor T mu on the right-hand side. We want to find solutions to these equations that are dynamic, but to simplify the problem, we make some additional assumptions, namely that we want to study solutions which are homogeneous and isotropic. We found that the last two assumptions, namely homogeneous and isotropic conditions, can be captured by a particular metric ansatz that is given by the FLRW metric that is reproduced in equation 35.2 here. Note that this parameter kappa here denotes or delineates three different cases, the one where kappa is negative, 0, or 1, and these will have important consequences for the global geometry of the universe that we can be studying. Of course, besides the geometry, we also need the input for the matter part for the universe. This means we have to specify the form of the energy momentum tensor T mu. Since we are interested in doing cosmology, it is perfectly fine to consider long timescales such that the matter can be assumed to be locally in thermal equilibrium. In addition, as a simplifying assumption, we can assume the local gradients to be small. That means that the local derivative of velocities can be small, and the local curvature, such as the Ricci curvature, can be small. With these two assumptions, we get a so-called perfect fluid or perfect ideal hydrodynamic form of the energy momentum tensor that was derived back in lecture 15. And the form of the energy momentum tensor is as follows. It has two terms, one that is symmetric in the fluid velocity u, and another term that is proportional to the metric tensor G mu. And these two terms come with coefficients where epsilon is the energy density, P is the pressure, and those would be the energy density and pressure of the matter that we want to study. The energy momentum tensor is covariantly conserved, so the geometric covariant derivative of the energy momentum tensor vanishes. If the energy momentum tensor is of the perfect fluid form, you can plug this into the conservation equation and show that this implies the equation of motion for the matter part, which is reproduced here in equation 35.6. For a universe that is isotropic and homogeneous, there is nothing that can move, because if it's moving, it cannot be isotropic and homogeneous. So the fluid velocity must have the form of 1 and 0, and that again simplifies the equations of motion. In particular, if we plug this into the equation 35.6 and we use the FLRW metric to calculate the Christoffel symbols that come from this covariant derivative of the fluid velocity here, the matter equation boils down to the equation 35.8. It's a first order differential equation in the energy. It's ordinary differential equation in the energy, and it will need an equation of state, meaning a relation between the pressure and the energy density as an input. Since this equation here depends on the matter part, so the energy density and the pressure, but also on this factor A here that is part of the metric ansatz, we cannot solve this equation without providing input for the geometry or the metric. In order to do this, we need a second equation that tells us how the geometry acts to matter content, and that is, of course, the field equations from GR. So the field equations from GR are reproduced here. I will note for further discussion that it is customary in cosmology to put the cosmological constant term inside the energy momentum tensor. So if I put this on the right-hand side and define the right-hand side as a new energy momentum tensor T hat, I can do that if the new energy momentum tensor is the old energy momentum tensor minus lambda over 8 pi g times g mu nu. So if I use the perfect fluid part for the energy momentum tensor T mu nu, that means that I get a term that has, if you want, an effective pressure that contains the cosmological constant. We will use that later. For now, let's just stick with the standard form of the Einstein field equations, and let's look at the 0, 0 component of this. We can use the well-known computer manipulation software to get the Ricci tensor, Ricci scalar, and Christophel's for the FLRW metric. If we do so, then plugging this into the equation above simplifies in the following form. So it becomes an ordinary differential equation for this factor A here that is linked to the local energy density epsilon. These equations here are known as the Friedmann equations of cosmology, and together with the meta equations provide the backbone for doing cosmology. So to summarize, we have found two equations of motions, one for the meta part, which we used the perfect fluid form of the energy momentum tensor for, and one for the geometry part, which are just the Einstein equations. And these two equations are reproduced here in equation 35.14. These are two coupled nonlinear ordinary differential equations. It is customary to furthermore introduce a shorthand notation to sort of make them appear simpler. The way we'll do this is that we notice that in these equations, the derivative of A always appears in this form A prime over A. So we introduce a shorthand notation A prime over A to be denoted by H of t. If we do that, then the form of the equations looks simpler. So it becomes the following form here, where remember that H here is now this derivative here. And again, just to reiterate, cosmologists like to redefine energy density and pressure by writing the following combinations in terms of new energy density and new pressure. So energy density plus cosmological constant is new energy density. Pressure minus cosmological constant is new pressure. So a way to interpret this is to say that these new epsilon hats and p hats are the energy density and pressure of matter, including the vacuum contributions. Vacuum, because if I don't have energy density and don't have pressure, I just have vacuum, and I still get non-vanishing values for epsilon hat and p hat here. In terms of these, then the equations of motion become even simpler. They are just written in equation 35.18. But I should be pointing out that it is an open problem to figure out what exactly the energy density and the pressure of the vacuum is, because we have a notorious problem with calculating these objects from our current theories of quantum field theory. We typically cannot successfully calculate something for lambda that would match observational data, but more on that later. So these equations in 35.18 are the equations, the basic equations of cosmology, and in the following lectures we will study their consequences.